Picture this, a world without zero, where computers can't function, where bridges collapse under faulty calculations, and where space travel remains a distant dream. This could have been our reality if not for the genius of ancient Indian mathematicians. Hidden in the pages of history are 30 brilliant minds whose secrets still power our modern world. From the concept of zero to the foundations of calculus, these forgotten pioneers shaped mathematics in ways that echo through time. But how did they crack codes that took the West centuries to rediscover? Why were their methods so far ahead of their time? And most importantly, where do we still use their breakthroughs today? The answers lie in dusty manuscripts and temple carvings, waiting to reveal how ancient India gave us the mathematical language of the universe. Stay with us as we unravel these 30 game-changing secrets, each one a testament to human ingenuity that continues to shape your daily life in ways you never imagined. By the end of this journey, you'll see numbers differently, discovering how your smartphone, your GPS, even your bank account all depend on discoveries made over 1,000 years ago under the Indian sun. The past isn't just history, it's the invisible code running our modern world. Now, let's step into the world of Aryabhata, a name that echoes through the corridors of mathematical history. Born in the 5th century, this visionary didn't just crunch numbers, he rewrote the rules of mathematics itself. Imagine a time when the concept of zero was just a blank space, a mystery waiting to be solved. Aryabhata didn't just fill that space, he gave it meaning, laying the groundwork for everything from your smartphone to space exploration. But his genius didn't stop there. He calculated pi with astonishing accuracy, landing on a value so close to what we use today that it's hard to believe it came from over 1,500 years ago. And trigonometry, Aryabhata's sine tables were so precise that modern astronomers still marvel at their accuracy. His astronomical theories, like the Earth's rotation on its axis, were centuries ahead of their time, challenging the very way humanity saw the cosmos. From the algorithms in your computer to the satellites orbiting above us, Aryabhata's fingerprints are everywhere. His work wasn't just ahead of its time, it was timeless. And as we'll see next, his legacy didn't just fade into history, it became the foundation for the mathematics we rely on every single day. But Aryabhata's brilliance didn't just stop at groundbreaking discoveries, it shaped the very way we learn math today. Take his trigonometric tables, for example. Those sine and cosine values you memorized in school, they trace their roots back to Aryabhata's meticulous calculations. His methods for solving triangles weren't just accurate, they were revolutionary, forming the backbone of modern trigonometry. And let's talk algebra. Aryabhata's techniques for solving equations were so elegant that they're still taught in classrooms, simplifying complex problems into steps anyone can follow. But perhaps his most astonishing contribution was hinting at the foundations of calculus centuries before Newton or Leibniz. His work on infinitesimals and changing quantities laid the groundwork for what would later become integral calculus. Think about that the next time you solve a calculus problem. You're using ideas that a 5th century genius first dreamed up. From the blackboards of schools to the cutting edge of scientific research, Aryabhata's legacy isn't just preserved, it's alive, evolving, and still teaching us new ways to see the world through numbers. And as we'll soon discover, his ideas were just the beginning of a mathematical revolution that would span centuries. Now, let's turn our attention to another towering figure in the world of mathematics, Brahmagupta. While Aryabhata laid the groundwork, Brahmagupta took those ideas and pushed them even further, especially in the realm of algebra, his most famous contribution. Giving zero its rightful place in mathematics, before Brahmagupta, zero was just a placeholder, but he defined it as a number with its own properties, like adding zero to a number leaves it unchanged. And that's not all, he also introduced rules for negative numbers, something that was revolutionary at the time. Imagine trying to solve equations without these concepts. It's almost unthinkable today. But Brahmagupta didn't stop there. His work on quadratic equations was nothing short of genius. He developed systematic methods to solve them, techniques that are still taught in classrooms and used in engineering fields today. Whether it's calculating trajectories in aerospace or optimizing structures in civil engineering, Brahmagupta's equations are at the heart of it all. His brilliance didn't just shape math, it built the frameworks that modern technology relies on. And as we'll see next, his influence extended even further into the hidden patterns of numbers. Now let's dive deeper into Brahmagupta's genius this time, exploring his groundbreaking work in number theory. One of his most remarkable contributions is the Brahmagupta Fibonacci identity, a mathematical gem that connects algebra and number theory in a way that still astonishes mathematicians today. At its core, this identity reveals how the product of two sums of squares can itself be expressed as a sum of squares, a concept that might sound abstract, but has very real-world implications. What's fascinating is how this identity, discovered centuries before Fibonacci, found its way into modern cryptography. Think about the secure transactions you make online. Every time you send encrypted data, algorithms rooted in number theory keep that information safe. Brahmagupta's identity plays a subtle but crucial role in these systems, helping to create the complex equations that protect our digital world. It's a perfect example of how ancient insights continue to shape cutting-edge technology. But Brahmagupta didn't just stop at identities. His work on Diophantine equations, problems seeking integer solutions, laid the foundation for entire branches of modern mathematics. These equations are now vital in fields like coding theory and even satellite communications, proving that his ideas weren't just ahead of their time, they were timeless. As we move forward, we'll see how another brilliant mind, Bhaskara I, built upon these very foundations to push mathematics even further. Now, let's shift our focus to another towering figure in ancient Indian mathematics, Bhaskara I. While his name might not be as widely recognized as some of his successors, his contributions were nothing short of revolutionary, especially in the realm of trigonometry. One of his most enduring legacies is his sign approximation formula, a mathematical breakthrough that simplified complex calculations centuries before computers existed. What made Bhaskara's formula so remarkable was its elegance and precision. He devised a way to approximate the sign of an angle using a simple ratio, allowing mathematicians and astronomers to bypass laborious geometric constructions. This might sound like a small step, but in an era when every calculation was done by hand, his method saved countless hours of work. Fast forward to today, and you'll find his principles embedded in the very algorithms that power modern computers. Think about the graphics in your favorite video game or the simulations used in engineering. They rely on lightning-fast trigonometric calculations. Bhaskara's approximation formula, refined over the centuries, helps computers perform these operations with astonishing speed. It's a perfect example of how ancient ingenuity continues to drive modern efficiency. But Bhaskara didn't just stop at approximations. His work also laid the groundwork for later mathematicians to refine trigonometric tables, making them more accurate and accessible. As we'll soon see, his ideas didn't just influence his contemporaries, they set the stage for even greater discoveries in the centuries to come. Now, let's turn our attention to Bhaskara II, a mathematician whose brilliance took the foundations laid by his predecessors to astonishing new heights. While Bhaskara I revolutionized trigonometry, Bhaskara II made groundbreaking strides in calculus centuries before Newton and Leibniz. His work on differential calculus, particularly his intuitive grasp of infinitesimal changes, laid the groundwork for what we now recognize as derivatives. Imagine the motion of a planet or the curve of a bridge. Bhaskara's insights into rates of change are what allow modern engineers and scientists to model these phenomena with precision. One of his most ingenious contributions was the Chakravala method, a revolutionary approach to solving equations that still baffles mathematicians with its elegance. Unlike brute force methods, Bhaskara's technique cleverly cycled through approximations to land on exact solutions, a principle that echoes in today's optimization algorithms. Whether it's streamlining supply chains or fine-tuning machine learning models, his 700-year-old strategy helps computers think efficiently. But what's truly remarkable is how Bhaskara's work transcended pure theory. His calculus wasn't just abstract, it was deeply practical, solving real-world problems in astronomy and architecture. For instance, his precise calculations of planetary motion weren't just academic exercises, they guided temple constructions and agricultural calendars. Today, that same blend of theory and application lives on in fields like robotics and economics, where optimizing resources is paramount. As we'll see next, Bhaskara's genius didn't stop at calculus. His astronomical models were equally visionary, bridging the gap between mathematics and the cosmos. Now, let's journey beyond the realm of equations and into the stars, where Bhaskara II's genius truly shines. His astronomical models weren't just ahead of their time. They were eerily precise, mirroring principles we now take for granted in modern celestial mechanics. Take planetary motion, for example. While many of his contemporaries relied on mythological explanations, Bhaskara calculated the orbits of planets using mathematical rigor, accounting for elliptical paths long before Kepler's laws. His work on the Earth's rotation even hinted at the concept of gravity, centuries before Newton's apple famously fell. What's fascinating is how Bhaskara's tools for tracking celestial bodies still resonate today. His sine tables and differential techniques allowed him to predict eclipses and planetary positions with startling accuracy, methods that modern astronomers refine with computers but still follow in spirit. Think of it like this: when NASA plans a Mars rover landing, they rely on the same foundational ideas of motion and trajectory that Bhaskara penned on palm leaves in the 12th century. But perhaps his most enduring legacy lies in bridging observation with calculation. Unlike armchair theorists, Bhaskara tested his models against the night sky, adjusting his math to match reality, a practice now central to astrophysics. From satellite launches to deep space navigation, his blend of curiosity and computation remains a guiding light. And as we'll soon discover, this wasn't the end of India's mathematical marvels, just a stepping stone to even more hidden treasures. Now, let's turn our attention to a mathematician whose ideas were so ahead of their time. They laid the groundwork for the digital age itself, Pingala. While many credit Gottfried Leibniz with inventing the binary number system in the 17th century, Pingala had already described it over 2,000 years earlier. His work on poetic meters in the ancient text Chanda Shastra revealed something extraordinary, a system of short and long syllables that functioned just like the zeros and ones we use in modern computing. Pingala's binary approach wasn't just theoretical. He even devised a method similar to the Fibonacci sequence to calculate combinations of these syllables, essentially creating an early form of combinatorial mathematics. Fast forward to today, and you'll find his principles alive in every computer circuit, where binary code powers everything from smartphones to space missions. But here's where it gets even more fascinating. His ideas also echo in Morse code. The dots and dashes, much like Pingala's short and long syllables, rely on binary patterns to transmit information across vast distances. What makes Pingala's story remarkable is how a study of poetry unlocked a universal language of logic. While his contemporaries focused on verse, he saw numbers hiding in the rhythms, a vision that would one day reshape the world. And as we'll soon see, this interplay of creativity and calculation didn't end with him. It only grew richer with the mathematicians who followed. But Pingala's genius didn't stop at binary code. His exploration of poetic rhythms unlocked another mathematical treasure: combinatorics, the science of counting possibilities. In the Shanda Shastra, he didn't just catalogue syllables, he calculated how they could combine, much like solving a puzzle. For example, to determine the number of ways short and long syllables could form a verse, Pingala devised rules that mirrored what we now call the binomial theorem. Think of it like finding all the possible paths in a maze. His methods mapped out every poetic pattern with precision. This wasn't just about poetry. His work became the foundation for probability theory centuries later. When mathematicians like Pascal and Fermat developed the rules of chance in the 17th century, they were unknowingly walking a path Pingala had paved. Today, his combinatorial principles help predict outcomes in fields from genetics to finance. Ever wondered how algorithms recommend your next favorite song or how insurance companies assess risk? Those calculations trace back to a scholar who saw numbers dancing in the rhythms of ancient verse. What's truly striking is how Pingala blurred the lines between art and science. While poets reveled in beauty, he uncovered the hidden equations behind it, a reminder that inspiration often strikes where we least expect. And as we'll see next, this tradition of interdisciplinary brilliance only deepened with the mathematicians who followed. Now, let's turn our attention to another towering figure, Varahamihira, a scholar whose work bridged worlds. While Pingala was decoding poetry, Varahamihira was mapping the stars, blending Greek and Indian astronomy into something revolutionary. His masterpiece, the Pankasiddhantika, wasn't just a collection of theories, it was a cosmic conversation. Imagine taking the best ideas from two ancient civilizations and weaving them into a single, precise system for predicting eclipses and planetary movements. That's exactly what Varahamihira achieved. His contributions to trigonometry were equally groundbreaking. He refined sine tables with astonishing accuracy, calculations so reliable they guided navigators and astronomers for centuries. Picture sailors relying on his math to cross oceans or farmers using his predictions to time harvests. This wasn't just abstract science, it was life-changing knowledge. And here's the fascinating part. While Greek astronomers like Ptolemy were working with chords, Varahamihira's sine functions offered a simpler, more elegant tool, one that's still taught in classrooms today. But what truly set him apart was his open-mindedness. At a time when cultures often clashed, he saw collaboration as the key to progress. The Pankasiddhantika didn't dismiss foreign ideas, it honored them, proving that the pursuit of truth knows no borders. As we'll soon see, this spirit of exchange would inspire generations of mathematicians to look beyond horizons, both earthly and celestial. Now, let's step into the world of algebra with Sridhara, a mathematician whose genius simplified one of the most daunting challenges in math: quadratic equations. While Varahamihira was mapping the stars, Sridhara was crafting rules that would make algebra more accessible for centuries to come. His systematic approach to solving quadratic equations was nothing short of revolutionary. Here's how it worked. Sridhara laid out clear, step-by-step methods to find the roots of quadratic equations, breaking down complex problems into manageable parts. Think of it like a recipe: follow the steps and you'll arrive at the solution every time. His rules were so effective that they became the foundation for the quadratic formula we still teach today. Imagine a classroom where students no longer had to guess or rely on trial and error. Thanks to Sridhara, algebra became a precise, logical process, but his influence didn't stop there. Sridhara's work also introduced early concepts of algebraic operations, like moving terms from one side of an equation to another. This might seem basic now, but back then it was a game changer. Engineers, architects, and even merchants used his methods to solve real-world problems, from calculating land areas to optimizing trade deals. What's truly remarkable is how timeless his contributions are. Modern textbooks may use different symbols, but the core logic remains Sridhara's. Next time you solve a quadratic equation, remember, you're using a method refined over 1,000 years ago, proof that great math never goes out of style. Now, let's journey further into the realm of mathematical brilliance with Madhava of Sangamagrama, a name that might not be as familiar as Newton or Leibniz, but whose discoveries were just as groundbreaking. While Europe was still centuries away from calculus, Madhava was already unraveling the secrets of infinite series, laying the foundation for one of the most powerful tools in modern mathematics. Madhava's most astonishing contribution was his infinite series for pi, a formula that could calculate the value of pi with unprecedented accuracy. Picture this: by adding and subtracting fractions in a specific pattern, he could approximate pi to as many decimal places as needed. This wasn't just a theoretical curiosity, it was a practical breakthrough that transformed astronomy, navigation, and engineering. His work on trigonometric functions like sine and cosine was equally revolutionary. He derived infinite series for these functions, essentially creating a blueprint for calculus long before it was formally invented. What makes Madhava's discoveries even more remarkable is how they mirror modern techniques. Today, computers use similar infinite series to calculate values for everything from satellite trajectories to financial models. Engineers rely on these methods to design bridges, while physicists use them to simulate the behavior of particles. Madhava's insights were so ahead of their time that when Europeans later developed calculus, they were unknowingly rediscovering ideas he had already explored. The legacy of Madhava's work is a testament to the timeless nature of mathematical truth. Whether it's predicting the motion of planets or optimizing algorithms, his infinite series continue to shape our world in ways he could never have imagined. And that's the beauty of math: it transcends time, connecting the genius of the past with the innovations of today. But Madhava's brilliance didn't stop with his own discoveries. He sparked a revolution by founding the Kerala School of Astronomy and Mathematics, a gathering of scholars who pushed the boundaries of knowledge even further. Imagine a place where, centuries before Newton penned his groundbreaking work, mathematicians were already unraveling the mysteries of calculus. That's exactly what happened in this vibrant intellectual hub along India's southwestern coast. The Kerala School didn't just build on Madhava's ideas, they refined them into a full-fledged system. Take infinite series, for example. While Madhava laid the foundation, his followers like Nilakantha Somayaji and Jayashtadeva expanded these concepts, developing methods to calculate everything from planetary positions to the precise length of a curve. Their work wasn't just theoretical, it had real-world applications, from predicting eclipses to designing intricate temple architecture. What's truly astonishing is how closely their techniques resemble modern calculus. They used iterative methods to approximate values, a cornerstone of today's numerical analysis. They even had early versions of differentiation and integration, tools we now rely on for everything from physics to economics. Yet for centuries, their contributions remained hidden, overshadowed by the later European developments. The Kerala School's legacy is a reminder that genius knows no borders. Their discoveries, though rooted in ancient India, echo through modern classrooms and laboratories worldwide. So the next time you hear about Newton or Leibniz, remember, the seeds of calculus were sown much earlier in the brilliant minds of Madhava and his Kerala School. And that's a story worth celebrating. Now, let's turn our attention to one of Madhava's brightest successors, Nilakantha Somayaji. While the Kerala School was a hub of innovation, Nilakantha stood out for his razor-sharp precision in modeling the cosmos. He didn't just accept earlier theories, he tested them, refined them, and often rewrote them entirely. His most groundbreaking work, a planetary model so accurate it rivaled the calculations of astronomers centuries later. Nilakantha's genius lay in his ability to build on Madhava's infinite series while adding his own revolutionary twists. Take his series expansions for trigonometric functions. He didn't just stop at approximations. He fine-tuned them to deliver astonishing accuracy, correcting errors that had persisted for generations. Imagine a mathematician in the 15th century calculating the positions of planets with near-modern precision, all without telescopes or computers. That was Nilakantha's everyday pursuit, but his contributions didn't end there. He challenged the long-held belief that planets moved in perfect circles, proposing instead a model where they traveled in epicycles, a concept later echoed by European astronomers like Copernicus. What's remarkable is how his methods mirrored calculus, using iterative corrections to inch closer to perfection. Today, engineers and physicists use similar techniques to simulate everything from satellite orbits to climate patterns. Nilakantha's story is a testament to the power of curiosity and refinement. He didn't just inherit knowledge, he pushed it forward, proving that even the boldest ideas can be polished to brilliance. And as we'll see next, his work set the stage for another visionary in the Kerala school, one who would compile these discoveries into the world's first calculus textbook. Now, stepping into the world of iterative problem solving, we encounter Parameshvara, a mathematician whose methods bridged ancient insight with modern computational power. While Nilakantha refined cosmic models, Parameshvara tackled equations with a relentless precision that feels almost algorithmic. His approach, iteration, a process of repeated refinement that inches closer to perfection with each step. Picture this: you're trying to solve a complex equation, but instead of guessing wildly, you make small, calculated adjustments, each one nudging you toward the correct answer. That's the essence of Parameshvara's method. He didn't just solve equations, he engineered a system to solve them more efficiently, laying groundwork that would later become the backbone of numerical analysis. Today, this same strategy powers everything from weather forecasting to stock market predictions, where approximations need constant tweaking to match reality. What set Parameshvara apart was his knack for recognizing patterns in error. He observed that each failed attempt wasn't just a dead end, it was a clue. By analyzing these missteps, he could adjust his next move, transforming trial and error into a disciplined science. Modern engineers rely on this very principle when designing algorithms for machine learning or optimizing flight paths for spacecraft. But here's the twist: Parameshvara's work wasn't just about numbers. It was a philosophy of patience and progress. In a world that often prizes instant solutions, his iterative methods remind us that some truths are uncovered slowly, one careful step at a time. And as we'll soon see, this mindset would inspire yet another Kerala school pioneer, one who dared to compile these mathematical secrets into a textbook centuries ahead of its time. Now, shifting our focus to the fascinating world of patterns and puzzles, we meet Narayana Pandit, a mathematician whose love for order and symmetry birthed innovations still shaping modern puzzle design. While Parameshvara refined iterative methods, Narayana turned his attention to combinatorial mathematics, exploring how numbers could dance together in perfect harmony. His most enduring legacy: magic squares, grids where numbers add up to the same sum in every row, column, and diagonal. Imagine a puzzle where every piece fits not just by chance but by a hidden logic. Narayana didn't just create these squares, he decoded the rules governing them, revealing how numbers could be arranged to meet this magical condition. Today, his work inspires everything from Sudoku to advanced algorithms in computer science, where balancing constraints is key. But Narayana's genius went beyond mere grids. He studied how objects could be combined, arranged, and counted, laying the groundwork for combinatorial mathematics. Think of it as the science of possibilities, whether it's shuffling a deck of cards or designing a secure password. His insights into permutations and combinations echo in fields as diverse as cryptography, genetics, and even game theory. What makes Narayana's magic squares truly timeless is their blend of art and logic. They're not just mathematical curiosities, they're exercises in creative problem solving. modern puzzle designers still draw from his principles, crafting challenges that tease the mind while adhering to his ancient rules. And as we'll soon discover, this interplay of numbers and imagination would inspire yet another mathematician, one who uncovered Fibonacci's sequence long before Fibonacci himself. Now, let's turn our attention to another hidden gem in the world of numbers, Gopala, a mathematician who uncovered the secrets of the Fibonacci sequence centuries before Fibonacci himself. While Narayana Pandit was weaving magic squares, Gopala was studying the rhythmic patterns of nature, noticing how certain numbers appeared again and again in the world around him. Gopala's work focused on what we now call the Fibonacci sequence, where each number is the sum of the two preceding ones, starting from 0 and 1. But here's the twist: he described this pattern long before it was popularized in the West. His observations weren't just theoretical. He saw these numbers reflected in the spirals of flower petals, the arrangement of leaves on a stem, and even the branching of trees. Nature, it seems, had been following Gopala's math all along. Today, the Fibonacci sequence is everywhere, from the algorithms that power stock market predictions to the designs of computer networks optimizing efficiency. Artists and architects use it to create visually pleasing proportions, while biologists study it to understand growth patterns in living organisms. Gopala's insights laid the groundwork for all of this, proving that mathematics isn't just about abstract ideas, it's woven into the fabric of reality itself. What's truly remarkable is how Gopala's discoveries bridge the gap between math and the natural world. His work reminds us that the most profound truths often hide in plain sight, waiting for a curious mind to uncover them. And as we'll soon see, this connection between numbers and nature would inspire yet another mathematician to explore the rhythmic patterns of life in a whole new way. Now, let's journey into the world of rhythm and melody, where mathematics and music intertwine through the work of Hemachandra. Just as Gopala uncovered the Fibonacci sequence in nature, Hemachandra discovered these same numerical patterns in the art of poetry and music. His fascination with rhythmic structures led him to explore how syllables and beats could be arranged in compositions, revealing a hidden mathematical harmony. Hemachandra's studies focused on the ways certain patterns repeat in poetic meters, much like the Fibonacci sequence repeats in nature. He found that the number of possible rhythmic combinations followed the same progression: 1, 1, 2, 3, 5, and so on. This wasn't just a coincidence, it was a universal principle echoing through both art and science. Today, musicians and composers use these very patterns to create captivating rhythms, from classical Indian ragas to modern electronic beats. What makes Hemachandra's work so fascinating is how it bridges disciplines. His insights didn't just stay confined to mathematics, they spilled into the creative arts, proving that numbers and notes share a deep connection. Whether it's the structure of a symphony or the cadence of a spoken verse, his discoveries continue to influence how we understand and create music. And as we'll see next, this interplay between calculation and creativity would inspire even more groundbreaking ideas in the centuries to come. Turning our attention to the stars, we meet Govindaswamy, a mathematician who took Aryabhata's groundbreaking work and sharpened it to near perfection. While Aryabhata laid the foundation with his sine tables, Govindaswamy recognized that even the smallest adjustments could make a world of difference, especially when it came to navigating the vast oceans or tracking celestial movements. Govindaswamy's refinements were all about precision. He recalculated Aryabhata's sine values with meticulous care, correcting subtle errors and fine-tuning the tables to reflect more accurate measurements. This wasn't just academic nitpicking, it had real-world consequences. Sailors and astronomers relied on these tables to determine latitudes, plot courses, and predict planetary positions. A slight miscalculation could mean the difference between reaching a distant port or getting lost at sea. What's remarkable is how his improvements echoed far beyond his time. Modern trigonometry still builds on these very principles, and the same attention to detail governs everything from satellite navigation to architectural engineering. Govindaswamy's work reminds us that progress often comes from refining what already exists, turning good ideas into timeless tools. And as we'll soon see, this pursuit of precision would inspire yet another leap forward in the hands of the next visionary mathematician. Now let's step into the world of shapes and lines with Shankaracharya, a thinker who saw geometry not just as numbers on a page but as a language of the universe itself. While others were busy with calculations, Shankaracharya focused on the elegance of proofs, crafting logical arguments that could stand the test of time. His work wasn't about reinventing the wheel, it was about understanding why the wheel worked so perfectly in the first place. Shankaracharya's geometric proofs were masterclasses in clarity. He took complex ideas like the properties of triangles and circles and broke them down into step-by-step reasoning that even a student today could follow. What made his approach revolutionary was how he connected these shapes to deeper philosophical truths, blending mathematics with metaphysics. For him, a circle wasn't just a curve, it was a symbol of infinity with no beginning or end. This philosophical precision didn't just stay on paper. His methods quietly shaped the foundations of modern Euclidean geometry, the same system taught in classrooms worldwide. Architects still rely on his principles when designing structures, and engineers use his proofs to ensure stability in everything from bridges to satellites. Shankaracharya's legacy is a reminder that the best mathematics doesn't just solve problems, it reveals the hidden order of the world around us. And as we'll discover next, this quest for order would take another bold turn with the insights of our next mathematician. Now, let's turn our attention to Mahavira, a mathematician whose work on algebra and fractions laid the groundwork for how we teach basic math today. While others were solving equations, Mahavira was busy simplifying them, creating rules that made complex problems accessible to everyone. His genius wasn't just in finding answers, it was in crafting methods so clear and logical that they became the backbone of early math education. Mahavira's algebraic solutions were ahead of their time. He didn't just tackle equations, he organized them into categories, providing step-by-step techniques to solve each type. Think of it like a recipe book for math. Every problem had its own method, and Mahavira made sure even beginners could follow along. His rules for fractions in particular were revolutionary. He showed how to add, subtract, and simplify them with such precision that his techniques are still taught in classrooms centuries later. What's fascinating is how practical his work was. Traders used his fraction rules to calculate profits, builders applied them to measure materials, and scholars relied on them for accurate calculations. Mahavira understood that math wasn't just for theorists, it was a tool for everyday life. His legacy lives on every time a student masters fractions or solves an algebraic equation, proving that the best ideas aren't just clever, they're timeless. And as we'll see next, this tradition of practical mathematics would continue to evolve with another brilliant mind. Moving from the practical algebra of Mahavira, we now uncover the brilliance of Yatavasabha, a mathematician who turned his gaze skyward. His groundbreaking work in spherical geometry didn't just solve abstract problems, it mapped the heavens with astonishing precision, laying the foundation for technologies we rely on today. Yatavasabha's insights into the curvature of the Earth and the movement of celestial bodies were centuries ahead of their time. He calculated angles, distances, and arcs on spherical surfaces with such accuracy that his methods echo in modern GPS systems. Think about it: every time your phone pinpoints your location, it's using principles of spherical geometry that Yatavasabha pioneered over 1,000 years ago. What set him apart was his ability to translate cosmic patterns into tangible mathematics. He didn't just observe the stars, he created frameworks to predict their paths, much like how GPS satellites calculate routes today. His work on three-dimensional space was so advanced that it blurred the line between astronomy and geometry, proving that the ancient world understood the interconnectedness of science long before modern textbooks defined it. The real marvel, Yatavasabha's theories weren't locked away in scrolls. They were used by navigators and architects, guiding ships across oceans and shaping structures that stood the test of time. His legacy is a reminder that the best ideas don't just belong to the past, they're the invisible threads stitching together our modern world. And as we'll soon see, this tradition of blending theory with real-world application would inspire yet another visionary mind. Now, let's turn our attention to Vaitsvara, a mathematician whose trigonometric breakthroughs became the backbone of early astronomy. While Yatavasabha mapped the heavens with geometry, Vaitsvara refined the tools needed to measure them. His trigonometric tables and formulas were so precise that they became indispensable for tracking planets and stars. Vaitsvara didn't just calculate angles, he redefined how astronomers understood motion in the sky. His sign tables, more detailed than any before, allowed predictions of celestial events with remarkable accuracy. Imagine ancient scholars using his work to forecast eclipses or chart planetary positions, long before telescopes existed. What made his approach revolutionary was its practicality. Vaitsvara's methods weren't confined to theory. They were adopted by temple architects to align structures with cosmic events and by navigators to guide ships under the night sky. His trigonometry bridged the gap between abstract math and the real world, much like how modern satellite systems rely on similar principles to function. Even more fascinating, Vaitsvara's work laid groundwork for later astronomers to build upon. His calculations influenced how cultures across Asia interpreted the cosmos, proving that mathematics is a universal language. As we'll see next, this interplay of numbers and stars would inspire yet another leap forward in our understanding of the universe. Moving forward in our journey through ancient Indian mathematics, we encounter Lala, a visionary whose work transformed how civilizations measured time. While Vaitsvara mapped the skies with trigonometry, Lala applied these principles to create precise calendars that synchronized with celestial cycles. His innovations weren't just theoretical, they dictated planting seasons, religious festivals, and even royal coronations. Lala's trigonometric tables were revolutionary. By refining sine and cosine calculations, he enabled ancient astronomers to predict lunar and solar eclipses with stunning accuracy. Picture this, centuries before mechanical clocks, Lala's formulas helped communities track months and years by observing the moon's phases and the sun's path. His methods were so reliable that they became the backbone of Hindu calendars still in use today. But Lala's genius extended beyond numbers. He understood that timekeeping was a bridge between heaven and earth. His texts, like the Sisyadhivedita Tantra, didn't just list equations, they explained how to apply them in daily life, from determining auspicious moments to navigating seasonal changes. This practicality made his work indispensable, much like how modern GPS relies on atomic clocks for precision. What's truly remarkable is how Lala's legacy endures. His trigonometric techniques influenced later scholars across Asia, proving that mathematics could harmonize human life with the cosmos. As we'll soon see, this interplay of time and calculation would inspire even more groundbreaking discoveries in the hands of the next mathematician. Now, let's turn our attention to Sankaracharya, a scholar whose work bridged the gap between ancient wisdom and modern discovery. While Lala mastered the art of timekeeping, Varya dedicated himself to unraveling the brilliance of Madhava's infinite series, a mathematical marvel centuries ahead of its time. His detailed commentaries didn't just preserve Madhava's work, they illuminated its depths, ensuring future generations could grasp its revolutionary potential. Sankaracharya's most significant contribution was his meticulous analysis of Madhava's series expansions for pi and trigonometric functions. Imagine this, long before European mathematicians like Newton and Leibniz formalized calculus, Varya was already explaining how these infinite series could approximate values with astonishing precision. His writings, such as the Yuktadipika, served as a guidebook breaking down complex concepts into step-by-step methods that even students today would recognize. But here's where it gets fascinating. Varya's commentaries weren't just historical footnotes, they became a lifeline for modern mathematicians. In the 20th century, scholars rediscovered his texts and realized Madhava's series, as interpreted by Varya, mirrored the foundational principles of calculus. This revelation rewrote the global narrative of mathematical history, proving that India's Kerala school had pioneered these ideas hundreds of years earlier. What makes Varya's legacy so enduring is his role as both a translator and an innovator. He didn't merely repeat Madhava's work, he refined it, adding his own insights that clarified its applications in astronomy and geometry. Today, his efforts remind us that mathematics is a living tradition where ancient secrets can resurface to inspire new breakthroughs. As we'll see next, this thread of discovery continues with even more astonishing contributions. Now, shifting our focus to another brilliant mind, we uncover the work of Nilakantha Somayaji, a mathematician whose geometric insights shaped not just theory but the very structures around us. While Sankara-Varya decoded infinite series, Nilakantha turned his attention to the elegance of shapes and spaces, crafting theorems that would leave a lasting mark on architectural design. Nilakantha's most notable contributions revolved around his geometric principles, which offered precise methods for constructing complex forms. His theorems weren't just abstract ideas, they were practical tools used by builders and architects of his time. For instance, his work on proportional relationships between geometric shapes allowed for the creation of temples and monuments with impeccable symmetry, a hallmark of ancient Indian architecture. What's truly remarkable is how these ancient techniques still resonate today. Modern architects studying traditional designs often stumble upon Nilakantha's principles, finding them surprisingly applicable even in contemporary projects. His understanding of spatial harmony and balance mirrors concepts now taught in advanced architectural courses, proving that his ideas were far ahead of their time. But Nilakantha's genius didn't stop at static structures. He also explored the dynamic interplay of light and shadow in geometric spaces, a concept that influences how modern buildings are designed to optimize natural lighting. This blend of mathematics and aesthetics showcases how deeply intertwined his work was with both art and science. As we move forward, we'll see how these geometric foundations paved the way for even more groundbreaking discoveries, connecting the dots between India's mathematical past and its enduring legacy in today's world. Now, let's turn our gaze skyward to Achyuta Pisaroti, a visionary who refined the way we understand the cosmos. While Nilakantha Somayaji mastered geometry on the ground, Achyuta's brilliance shone in the heavens, where he fine-tuned planetary models with astonishing precision. His work wasn't just theoretical, it had a practical magic, enabling him to predict eclipses with remarkable accuracy, a feat that left even his contemporaries in awe. Achyuta's refinements to existing astronomical models were groundbreaking. He corrected subtle errors in earlier calculations, accounting for the Moon's irregular orbit and the Sun's apparent motion with a level of detail that was unprecedented. These adjustments weren't mere tweaks, they were revolutionary, allowing for eclipse predictions that were reliable enough to be used in religious and agricultural calendars. Imagine the impact. Communities could plan ceremonies or harvests around these celestial events, thanks to Achyuta's mathematical foresight. What's even more fascinating is how his methods echo in modern astronomy. Today's scientists still rely on similar principles of orbital mechanics, proving that Achyuta's insights were centuries ahead of their time. His ability to blend observation with computation laid the groundwork for the precise celestial navigation we take for granted now. But Achyuta didn't stop there. He also documented his findings in clear, systematic ways, making them accessible to future generations. This commitment to sharing knowledge ensured that his refinements weren't lost to history, but instead became stepping stones for later astronomers. As we'll see next, this legacy of precision and innovation didn't end with a tutor. His work paved the way for even more daring explorations of the cosmos, bridging the gap between ancient wisdom and modern science. Now, let's step into the world of Jayashtadeva, a mathematician whose work reshaped how we teach and understand calculus. While Achyuta Pisarati perfected celestial predictions, Jayashtadeva turned his focus to the very language of change, mathematics itself. His masterpiece, the Yuktibhasa, stands as the first known textbook on calculus written centuries before Newton or Leibniz entered the scene. What makes the Yuktibhasa extraordinary is how it breaks down complex ideas into teachable concepts. Jayashtadeva didn't just scribble formulas, he explained the why behind them, offering proofs and step-by-step reasoning that made calculus accessible. Imagine a classroom in 16th century Kerala, where students grappled with infinite series and derivatives using methods so clear they're still admired today. One of his most groundbreaking contributions was his work on infinite series, specifically the series for pi and trigonometric functions. These weren't just abstract curiosities, they were tools for solving real-world problems from astronomy to architecture. The Yuktibhasa detailed how to sum an infinite sequence to approximate pi, a technique that mirrors modern calculus textbooks. But here's the twist: Jayashtadeva's approach was deeply intuitive. He used geometry to visualize calculus, a method that modern educators now champion to help students grasp abstract concepts. His emphasis on understanding over rote memorization set a gold standard for math pedagogy, one that resonates in today's classrooms where visual and intuitive learning are prioritized. The Yuktibhasa also bridged gaps between theory and application. It didn't just dwell on numbers, it showed how calculus could model planetary motion, optimize construction, and even predict tides. This practical bent foreshadowed how calculus is taught now, as a living, breathing tool, not just a set of rules. As we'll soon see, Jayashtadeva's legacy didn't stop with his textbook. His ideas sparked further innovations, proving that the best mathematical secrets aren't just solved, they're shared. Now, let's turn our attention to Kelala Nilakantha Somayaji, a brilliant mind who refined the work of his predecessors with remarkable precision. While Jayashtadeva laid the groundwork for calculus, Nilakantha Somayaji took on the cosmos, correcting and perfecting earlier astronomical models in ways that still align with modern data. His sharp eye for detail and relentless pursuit of accuracy set him apart as a true pioneer of celestial mathematics. Nilakantha Somayaji's most notable contribution was his revision of planetary motion theories. Earlier models, like those of Aryabhata, had gaps in predicting the movements of planets like Mercury and Venus. But Nilakantha Somayaji spotted these inconsistencies and introduced corrections that brought the calculations startlingly close to what we know today. His adjustments weren't just minor tweaks, they were revolutionary refinements that accounted for elliptical orbits centuries before Kepler formalized the idea. What's truly fascinating is how his methods mirrored modern computational techniques. He used iterative approximations, a process where he repeatedly adjusted his calculations to inch closer to the true values. This approach is eerily similar to how modern astronomers and spacecraft engineers refine trajectories today. His work on the moon's motion, for instance, was so precise that it reduced errors to a fraction of what earlier models had produced. But Nilakantha Somayaji didn't stop there. He also challenged the geocentric view, proposing a model where Mercury and Venus orbited the Sun, a concept that wouldn't gain widespread acceptance in Europe until Copernicus. His insights into the solar system's structure were groundbreaking, blending observation with mathematical rigor in a way that feels strikingly modern. Even more impressive is how his corrections stand the test of time. When modern astronomers revisited his calculations, they found his values for planetary positions matched contemporary data with astonishing accuracy. It's as if he had a window into the future of astronomy, bridging ancient wisdom and modern science. As we'll see next, his legacy didn't just influence astronomy, it paved the way for later mathematicians to push the boundaries even further, proving that the quest for precision is timeless. Now let's uncover the brilliance of Chitrabhanu, a mathematician whose solutions to complex algebraic problems remain a cornerstone in advanced mathematics even today. While Nilakantha Somayaji refined celestial calculations, Chitrabhanu turned his focus to the intricate world of algebra, tackling equations that seemed unsolvable in his time. His work didn't just solve problems, it laid down methods that mathematicians still reference centuries later. Chitrabhanu's genius shone brightest in his approach to indeterminate equations where multiple solutions are possible. He developed systematic techniques to find integer solutions to these equations, a method that mirrors modern Diophantine analysis. Imagine trying to solve a puzzle with endless possibilities. Chitrabhanu's methods provided a roadmap to narrow down the answers efficiently, a strategy still taught in higher-level algebra courses. One of his most celebrated contributions was his solution to the equation now known as the Pell's equation, though he solved it long before Pell's name was attached. His method involved recursive sequences, a concept that feels surprisingly contemporary. Today, this very approach is used in computer algorithms for cryptography and number theory, proving that his insights were centuries ahead of their time. But Chitrabhanu didn't stop at equations. He also explored combinatorial mathematics, finding patterns in numbers that others overlooked. His work on permutations and combinations laid groundwork that would later influence probability theory and even modern coding theory. It's as if he saw the hidden threads connecting numbers, weaving them into a tapestry that future mathematicians would unravel further. What makes his legacy enduring is how his solutions blend creativity with rigor. He didn't just find answers, he crafted elegant, repeatable methods that others could build upon. Modern mathematicians still revisit his texts, not just for historical curiosity, but for practical insights that spark new discoveries. As we move forward, we'll see how these algebraic foundations influenced later thinkers, bridging ancient ingenuity with the cutting-edge math of today. Now, let's shift our focus to Munishvara, a mathematician whose groundbreaking work on infinite series was so ahead of its time that Europe wouldn't catch up until centuries later. While Chitrabhanu mastered algebra, Munishvara ventured into the realm of infinite sums, uncovering patterns that would later become central to calculus. His insights weren't just theoretical, they were practical tools for solving real-world problems in astronomy and geometry. Munishvara's most notable contribution was his development of infinite series expansions, particularly for trigonometric functions like sine and cosine. He didn't just approximate these values, he derived exact formulas using iterative methods, a technique that feels strikingly modern. Imagine calculating the position of a planet or the length of a curve without calculators. Munishvara's series provided the precision needed for such tasks, and his methods were remarkably efficient. What's truly fascinating is how his work resurfaced in 18th century Europe, where mathematicians like Euler and Newton independently rediscovered similar series. Historians now argue whether these ideas traveled westward or emerged in parallel, but either way, Munishvara's brilliance is undeniable. His series expansions became foundational in calculus, enabling breakthroughs in physics, engineering, and even signal processing today. But Munishvara didn't stop there. He also applied his infinite series to planetary motion, refining models that predicted eclipses and celestial events with stunning accuracy. His work bridged the gap between abstract math and tangible results, proving that numbers could unlock the secrets of the cosmos. As we'll see next, these mathematical threads didn't just fade into history. they were picked up and woven into the fabric of modern science, proving once again how ancient Indian thinkers shaped the world we know today. Now, let's turn our attention to Kamalakara, a visionary who bridged the gap between Indian and Islamic astronomy, creating a unique fusion of knowledge that enriched both traditions. At a time when scientific ideas were often confined by geography, Kamalakara's work became a testament to the power of cross-cultural collaboration. His ability to synthesize diverse astronomical systems not only advanced the field but also laid the groundwork for a more interconnected scientific world. Kamalakara's most significant contribution was his seamless blending of Indian and Islamic astronomical techniques. He studied the works of Persian and Arab scholars, integrating their precise observational methods with India's rich theoretical frameworks. For instance, he adopted the Islamic Zijr detailed astronomical tables and combined them with traditional Indian planetary models. This hybrid approach produced calculations of unprecedented accuracy, particularly for predicting eclipses and planetary positions. What made Kamalakara's work revolutionary was its global perspective. He didn't just borrow ideas, he refined them, creating a unified system that transcended cultural boundaries. His treatise, the Siddhanta Tattva Viveka, became a cornerstone for later astronomers, showcasing how diverse traditions could complement each other. This exchange wasn't one-sided. His innovations also influenced Islamic scholars, creating a feedback loop that propelled astronomy forward. Beyond theory, Kamalakara's fusion had practical implications. His improved celestial models were used by navigators and timekeepers across Asia, demonstrating how shared knowledge could solve real-world challenges. Even today, historians see his work as an early example of global scientific cooperation, a reminder that progress often thrives at the intersection of cultures. As we'll soon discover, this spirit of exchange didn't end with Kamalakara. The next mathematician we'll explore took these interconnected ideas even further, preserving and translating knowledge for future generations. Now, let's step into the world of Jagannatha Samrat, a scholar whose work became a bridge between two great intellectual traditions. While Kamalakara fused Indian and Islamic astronomy, Jagannatha took a different but equally vital approach. He became a guardian of knowledge, ensuring that groundbreaking ideas weren't lost to time. Jagannatha's most enduring legacy lies in his translations. At a time when Arabic scientific texts were brimming with advanced mathematical concepts, he meticulously translated these works into Sanskrit, making them accessible to Indian scholars. One of his crowning achievements was rendering the Tauria al-Magisti, an Arabic version of Ptolemy's Almagest, into Sanskrit as the Siddhanta Samrat. This wasn't just a linguistic feat, it preserved critical astronomical theories that might have otherwise faded into obscurity. What set Jagannatha apart was his precision. He didn't merely translate words, he adapted complex ideas into frameworks familiar to Indian mathematicians. For example, he converted Arabic trigonometric functions into their Sanskrit equivalents, ensuring seamless integration with existing Indian methods. This careful work allowed later scholars to build upon both traditions without gaps or confusion. Beyond preservation, Jagannatha's translations sparked new innovations. By introducing Arabic algebra and geometry to Sanskrit audiences, he enriched India's mathematical landscape. His versions of these texts became standard references in medieval Indian universities, influencing generations of thinkers. Even today, historians credit him with keeping the dialogue between East and West alive during a pivotal era. As we'll see next, this tradition of blending and preserving knowledge didn't stop with Jagannatha. Another mathematician would soon emerge, reviving ancient Indian insights for a modern world, but that's a story for the next chapter. Now, let's turn our attention to Ramchandra, a visionary who breathed new life into ancient Indian mathematics during the 19th century. At a time when colonial education systems often overlooked India's rich mathematical heritage, Ramchandra became a torchbearer, bridging the gap between timeless traditions and the modern world. Ramchandra's most remarkable contribution was his effort to reintroduce classical Indian mathematical concepts to a new generation. He authored the first mathematics textbook in Hindi, a treatise on problems of maxima and minima, making advanced calculus accessible to students in their native language. This wasn't just about translation, it was a revival. He meticulously explained ancient techniques like Bhaskara II's differential calculus alongside contemporary European methods, showing how they complemented each other. What made Ramchandra's work groundbreaking was his ability to simplify complex ideas without losing their depth. For instance, he demonstrated how Madhava's infinite series for pi could be taught alongside Newton's calculus, revealing their shared foundations. His approach didn't just preserve knowledge, it made it relevant, proving that ancient Indian mathematics wasn't obsolete but rather a precursor to modern theories. Beyond textbooks, Ramchandra championed the integration of Indian mathematical thought into formal education. He argued that ignoring these traditions meant losing a wealth of insight, and his advocacy laid the groundwork for future scholars to explore these connections. Today, his efforts remind us that progress isn't just about new discoveries, it's also about rediscovering and honoring the wisdom of the past. As we prepare to meet our final mathematician, we'll see how this legacy of rediscovery reached its pinnacle with a genius whose work echoed the brilliance of his ancient predecessors. Now we arrive at the story of Srinivasa Ramanujan, a name that shines like a beacon in the world of mathematics. His journey is nothing short of miraculous, a self-taught genius whose work seemed to emerge from a deep connection with India's ancient mathematical traditions. Ramanujan's notebooks, filled with thousands of groundbreaking formulas, often appeared as if they were whispered to him by the past. Many of his discoveries, like his work on infinite series and modular forms, bore an uncanny resemblance to the techniques of mathematicians like Madhava and Bhaskara II. Yet he had little formal training in their works. This led scholars to wonder, was Ramanujan tapping into a collective mathematical intuition, one that had been nurtured in India for centuries? One of his most astonishing contributions was his mastery of continued fractions, a concept explored by ancient Indian scholars like Aryabhata. Ramanujan's formulas in this area were so advanced that mathematicians are still unraveling their depths today. Similarly, his insights into partition theory echoed the combinatorial brilliance of thinkers like Narayana Pandit, proving that India's mathematical heritage was alive in his mind. But perhaps the most striking link was his intuitive grasp of elliptic functions, a field where Madhava's Kerala school had laid foundational work centuries earlier. Ramanujan's theorems in this area were so profound that they reshaped modern number theory, yet they felt like a rediscovery of lost knowledge. Ramanujan's life was a testament to the enduring power of India's mathematical legacy. Though he worked in isolation for much of his career, his discoveries bridged the ancient and the modern, showing that the secrets of the past were never truly forgotten, they were waiting to be revealed again. And with that, we come full circle, seeing how these 30 mathematicians across millennia wove a tapestry of brilliance that still illuminates our world today. As we bring this journey to a close, it's remarkable to see how the brilliance of these 30 ancient Indian mathematicians continues to echo through time. Their secrets, whether it's Aryabhata's zero, Bhaskara's calculus, or Ramanujan's intuitive leaps, aren't just relics of the past. They're the invisible foundations of our modern world, shaping everything from computer algorithms to space exploration. Think about it. Every time you use GPS, you're relying on spherical geometry principles laid down by Yatavasabha. When you encrypt data online, Brahmagupta's number theory is working behind the scenes. Even the algorithms powering your smartphone owe a debt to Pingala's binary system, dreamed up over 2,000 years ago. These aren't just historical footnotes, they're living ideas still pushing humanity forward. What's even more inspiring is how these discoveries transcended borders and centuries. The Kerala school's calculus predated Newton by generations. Fibonacci's famous sequence had already been explored by Gopala. This isn't just India's heritage, it's a gift to the entire world, a testament to how knowledge knows no boundaries. So where do we go from here? The story doesn't end with these 30 names. Countless manuscripts still wait to be translated, and who knows what other mathematical treasures lie undiscovered. That's the real invitation here, to keep exploring, questioning, and marveling at how ancient insights still light our way. If this journey through India's mathematical legacy has sparked your curiosity, don't let it stop here. Dive deeper into these stories, share them, and let's keep this conversation alive. After all, the next great discovery might be hidden in an old palm leaf manuscript, or maybe, just maybe, it's waiting in your own imagination. If you enjoyed unraveling these mathematical mysteries with us, make sure to hit that like button, subscribe for more deep dives into history's hidden geniuses, and ring the bell so you never miss an episode. Who knows what other forgotten secrets we'll uncover together? Until next time, keep wondering, keep exploring, and remember, the past is always whispering to those who listen.